Radicals are expressions involving things like square roots or cubed roots, or more generally nth roots of real numbers. There's a bit of a dichotomy between whether or not you're talking about an even root or an odd root, and so it's a good idea to just review square roots, cubed roots, and then summarize at the end. So let's look at square roots of a real number. Just for an example, let's take square root of 2. Square root of 2 is a real number, and it has two defining characteristics. The first thing is that it is a non-negative real number. So by definition, when I take square root of a number, I'm asking for a non-negative real number. The second characteristic about the square root of 2 is that its square is 2. And that's exactly what we mean by the square root of 2. The non-negative real number whose square is equal to 2. So what do I mean by that? Well, if I take square root of 2, it's greater than or equal to 0. That means it's non-negative. And if I was to take square root of 2 and square it, I'll get 2 back. You can go to a calculator and get an estimate of square root of 2. So doing that, square root of 2 is about 1.414. And I hope you agree that the number it returned is indeed non-negative, greater than or equal to 0. And you can test it. You could take 1.414 and you could square it. And when you do that, you get about 1.999, pretty close to 2. And therefore, this looks like 1.414 is a good estimate of the square root of 2. Some numbers have very easy to compute square roots. For example, square root of 4 is easy to compute because 4 is a square. 4 is 2 squared, and we're taking the square root of that. And so, of course, it's going to be equal to 2. Again, this is true because 2, the result that I gave you, is greater than or equal to 0. It's a non-negative real number. And when I square it, I do get 4, which is what was under the radical. So square root of 4 truly is 2. You have to be very careful in applying the principle that we just applied above. If I see an expression like minus 2 and I'm squaring that and then take the square root, the temptation is to report minus 2 back. But the order of operation requires me to square that expression first and get 4. And now we're right back to where we were before. Square root of 4 is 2, positive 2. Notice that it doesn't give me negative 2 because it should be giving me a non-negative real number. That's how we define the square root. Now compare that situation to something like the square root of minus 4. So now I'm asking for a real number that's non-negative, and when I square it, it's going to give me minus 4. Well, that's a problem because no matter what I take for the answer, let's call it x, and I square it, it's supposed to be minus 4. You'll never be able to find a real number whose square is ever negative, let alone negative 4. So this equation here has no real number solutions, which means the square root of minus 4 can't possibly be defined. Has no meaning at this point. There's no real number whose square is negative 4. As a result, the square root of x is defined only for x greater than or equal to 0. Now you may be aware of imaginary numbers, of complex numbers, and that opens the door to writing down an expression for the square root of minus 4, but at this point there is no real number that would be the square root of negative 4. I did say here that it was defined for x greater than or equal to 0, and you should observe that square root of 0 makes perfect sense. Remember I said non-negative, not positive, non-negative, and in fact if I take 0 and square it, I will get 0 right back, so the square root of 0 is 0. Let's now look at cubed roots. So now, for example, if I take the cubed root of 8, well, that's 2, because if I take 2 and I cube it, I get 8 right back. Notice I wasn't here concerned about observing that 2 was a non-negative number, and in fact for cubed roots it really doesn't matter here. If I take the cubed root of minus 8, this is negative 2, because if I take minus 2 and cube it, I have an odd number of minus signs. One will survive when I multiply, and I'll get minus 8 back, which was what was under the radical sign. So there's a dichotomy here between odd and even roots. Here I'm in a cubed root case. I can't take the cubed roots of negative numbers because when I take an odd power of a real number that's negative, it will still be negative as a result. Cubed root of x is defined for all real numbers x. So in general, we can talk about nth roots of a real number. Here n is some positive integer like 2, 3, and higher. And we would write that as the nth root of x, and that satisfies the following property. When I take the nth root of x and I raise it to the nth power, I get x right back. But keep in mind there's this subtlety with the even case like we saw with n equal to 2, the square root case. If n is even, then this is only defined for x greater than or equal to 0. And the resulting answer that I get from my calculator when I ask it for the nth root of a number is something that's non-negative, greater than or equal to 0. If n is an odd root, then it's defined for all real numbers x. Okay, now let's return to a discussion about the laws of exponents, because that will play a role and connect exponents to radical expressions. And the first thing I want to look at here is a power of a power. And by that I mean something like 2 squared, and then I'm going to take a power of that, cube it, say. So what should I do with the exponent here when I take this power, 2 squared, and take a power of that? Well, let's write it out. It's 2 squared times 2 squared times 2 squared. So I'm just taking the number in parentheses and multiplying it by itself 3 times according to this exponent here. Well, that's going to be 2 plus 2 plus 2 factors of 2 that are showing up. I have 2 of them here, here, and here. So I'm just applying my principle of addition of exponents when I multiply the bases together. And that's 2 times, or that's 3 times 2 in the exponent. I have 1, 2, 3 terms. So 3 times 2. Of course, that's 2 to the 6th. So the answer is, if I take a power of a power, I just multiply the exponents together. Notice I could have done it in the other order. I could have 2 cubed and square that, and that means to take 2 cubed times itself twice. But the answer is still the same here. I'm just going to count it in a different way. I have 3 plus 3, and that still gives me 6. So what we're seeing here is a general rule. If I take b to the m and I raise it to the nth power, I can multiply those exponents m times n. And this is the same as b to the n to the m. Observe I've changed the order of the exponents because the order that I multiply m and n together really doesn't matter. I could put n first or m second, and I would have the same exponent. This is useful for us because it allows us to discuss what we mean when we talk about a rational exponent of a number. We've only at this point talked about taking exponents that are integers. We could deal with positive whole numbers, negative whole numbers, even 0. But a rational number, a fraction, what does it mean for that to be in the exponent? For example, what is 2 to the 1/3 supposed to represent? Well, if we don't know what it means, it at very least should be consistent with all the laws of exponents that we've seen. So for example, this one here, if I was to take 2 to the 1/3 and then cube it, if it's going to behave according to this property above, I should be able to multiply those two together. 3 times 1/3. When I multiply the exponents, I'll get an exponent of 1, and 2 to the 1st is just 2. So notice what happened here is I took this number, this mysterious number, 2 to the 1/3, and I cubed it, and I got 2 right back. This suggests that it's really the cubed root of 2, because cubed root of 2 is precisely the number that when I cube it, gives me 2 right back. So cubed root of 2 has this property, And 2 to the 1/3 has this property that when I cube it gives me 2. So this suggests that if I see something like b to the 1 over n, that this is just the nth root of b. And in fact, that's how we'll define it. There are some obvious concerns here. If n is even, b must be greater than or equal to 0. So I'm assuming b is greater than or equal to 0 for n even. As a special case, if I take the square root of b, that's with n equal to 2. We just don't write the 2 in the radical notation because it's such a common one. And that's b to the 1/2 power. And here I'm definitely assuming that b is non-negative. For example, now if I look at something that's a more general rational power like 3/2 in the exponent, so 4 to the 3/2, how might I interpret that? And the answer is to use the power of the power property again. It's 4 to the 1/2, and I'm cubing the results because multiplying these two exponents gives me 3/2. 4 to the 1/2 is the square root, and I'm cubing it. Again, just using this property or this property here for the n equal to 2 case. Order of operations says I'll do what's in the parentheses first. Square root of 4 is 2, and I cube the result, and I get 8. Notice this could have been done in the other order. I could have cubed it first and then raised it to the 1/2 power. But then I have to compute 4 cubed, which is 4 times 4, that's 16 times 4 is 64, and then take that to the 1/2 power, which means the square root of 64, which is still easy to figure out in your head, but not as easy as it was before. It's 8. So you can see the advantage of choosing the order to take the square root first to keep the number small and then cube. But they still result in the same answer. So one final law of exponents, if I raise b to a rational exponent, m over n, here m and n are integers, n is non-zero, or it'd be dividing by 0. How do we interpret that? It's the nth root of b to the nth power. Alternatively, it's b to the m, and take the nth root of that. Of course, if there's any issue with an even root, in which case b should be greater than or equal to 0. Let's now turn to powers of products. What I mean by that is something like a times b to the n. So now I'm taking a product and then I'm taking a power of it. Because the order that we multiply real numbers in doesn't matter, I could just apply the exponent to the a and apply the exponent to b, and I get the result. So power of a power is just a to the n times b to the n. Similar fact is true for ratios. If I have a over b and then I raise that result to the nth power, I could just do the numerator and the denominator separately and then divide the results. Be very careful here. If I take a plus b and I raise that to the nth power, so now I'm adding these two things together, that is not at all the same as taking a to the n and b to the n and adding the results together. Don't expect powers, which has something to do with multiplication, to be compatible with addition or subtraction. However, taking a power of an expression is compatible with multiplication and division, as illustrated by these properties here. Let's look at an example of what we've learned and finish the video here. So here I'm going to ask to evaluate 8 over 125, and then we're going to take that to the minus 2/3 power. Let's apply the laws of exponents to evaluate this expression completely. The first thing you might do is observe that the negative power corresponds to taking the reciprocal of the number. I'm going to do that right away and flip it over. 125 over 8, but now to the 2/3 power. Now I'll use the property that we just talked about. I can take the power of the numerator, I can take the power of the denominator and divide the results. And then we've discussed rational exponents. We can take the cubed root of 125 and then square the result, and the cubed root of 8 and square the result. Cubed root of 125 is 5 because 5 times 5 times 5 gives me 125, and I have to square that. Cubed root of 8 is 2, and I have to square that. And we're home free now. 5 squared is 25, and 2 squared is 4. Just to summarize here quickly, if you see a negative exponent, that means reciprocal. Flip it over. If you see a rational exponent, the denominator means a radical. In this case, 1/3 corresponded to cubed root. The 2 in the numerator just means to square it. Nothing special there.